we will start from current slide. Okay, a little bit on where we're going, what we're going to do, what order. Okay, for about the next 2 hours, or at least until 3:15 or so, we're going to continue in Chapter 6. We're currently on electric current. This section that we're doing is a fairly long section, but the first part of it is going to cover what we're going to do in today's lab. We may even get enough covered for Thursday's lab as well, because they're really closely related. But at 3:15, we'll stop and do today's lab. That's on electric currents. And then that probably won't take you 2 hours. And whenever you finish the lab, then we can come back to the classroom and you can take your test. Now, the test is on Chapter 4, the last chapter we finished, the heat and temperature chapter. The lab we're doing today is on Chapter 6, our first lab in Chapter 6. Now, just looking ahead, we'll have another lab in Chapter 6 on Thursday. I'm really sure we'll be ready for that one by then. And more than likely be then ready for, then the next Tuesday, have the last lab in Chapter 6, and we'll probably finish Chapter 6 that day as well. So then, shortly after that, we'll have the test in 6, and we'll move on to Chapter 8. And Chapter 8 is the last chapter we'll be doing, and will just be one lab in that, and then the test, and ultimately the final exam. Okay, and JJ came back. I marked you by mistake here, but you are here, so good. I knew you had been here. Okay. Now, I've asked the first two classes question, and I haven't gotten anything positive yet, so I have a feeling I know the answer, but let's just get it. Have y'all seen anything in your emails or anywhere else, any mention of the student course evaluation?
Yes, sir.
Oh, you have?
I done it already.
Huh?
I done it already.
When did that come out?
Yesterday.
Yesterday?
Yeah.
Okay.
On Monday.
Oh, okay. Because, well, yesterday was Monday. Okay.
Oh, yeah.
Yeah, okay. So, that I had asked the first two classes, and no one had seen or heard anything about it yet. But y'all have seen the student course evaluations. Okay, good. Please get those done. And thank you if you've already done them, and get them done as soon as you can. Now, well, if you want to wait and see what your final grade is, you can do them then. But please don't forget to do them, okay? Because I know how easy it is at the end of the term, after the finals, you're just wasted, and you forget to go back and do the student course evaluation. If there's any chance that's going to happen, go on and do it now while you're relaxed. You got plenty of time, and you can take care of it. So those are important. I do look at them very carefully. I look at my own to see places I can improve, but I also use it when I'm doing evaluations of other instructors that are under me. So it's certainly an important document. Don't discount it. It's an important deal. Justin Struthers here. All right. Any questions on anything we've done so far, or how we're going to proceed from here? Any questions whatsoever? All right. Evidently, y'all feel like it's pretty nice weather out there. It seems a little on the chilly side to me, but I'm okay if y'all are out. If I get to move around, y'all are sitting there. If anyone does want the windows closed, we can probably get them closed. So let me know. Okay? All right. We started in Chapter 6 last time, and we got, a fair amount done. We talked about charges in general, static electricity, electric potential, all sorts of things along those lines, electric forces, electric fields, those types of things. Now we're moving away from static electricity to moving electricity. In other words, charges that move, okay? And when you have a moving charge, we generally will call that a current, electric current. So earlier we talked about electrostatics, building up charge on a non-conductor or conductor, and then maybe discharging it, whatever. The charges are more or less fixed in place. They're not moving around, they just build up, and then they discharge, or not. Now we're going to allow those charges to move, and that is what defines an electric current. So basically, as I said, electric current is a flow of charge. Now, before when we talked about flow of energy, I said that's because they thought energy was some sort of fluid of some nature, some innocuous fluid. Here, this is a better term because charges are actually moving. Okay? At least somewhat moving, but maybe not in the sense of water flowing through a pipe. We make those analogies, but it's not quite the same. Why do the charges move? They say flow. Well, the last thing we talked about before was what we called electric potential. Okay? You have high potential here, low potential there. Just like we had when you hold the book up, high potential, drop it, it moves to a lower potential. When we're talking about heat and temperature, the vibrations of, say, an object that's warm are going to move, always moving from hot to cold. Okay? Everything moves down a gradient. Okay? And the gradient here is your potential difference. We have a little problem when it comes to electricity, though. We'll get to that in just a couple of minutes, but it's a little bit different from before. What are electric circuits? Okay, current is the flow of charge. Electric circuit is the structure designed to localize, I don't like utilize, but to use current. In other words, the pathways, you might say, through which the current flows. That will be our electric circuits. That's what we'll be building in today's lab. Okay? So let's look at electric circuit. Okay? This is the first subtopic on page 148. What do you need in any electric circuit? You've got to have something to make the move happen, to make the charge move. That's your voltage source. Voltage being your potential difference. Remember the unit for voltage? We talked about it last time, I think. Joules per coulomb, energy per charge. So it's the energy the charges have. You got to give them that in order for them to move. And that's what we say is the energy input. So voltage is charge per coulomb. Coulomb is, energy per charge, which is joules per coulomb. That's what a volt is. That's your energy input. You don't have the energy, there's not going to be any movement of charge. Okay? This is absolutely necessary for the continuing flow. You lose the potential difference, the flow stops. Okay? It can't go on its own. So, what are some of the circuit elements in your electric circuits? Well, the energy is used up as heat, light, work, so that is your, what we sometimes call the load. The light bulb, the projector, the computer, the space heater, whatever it is that's using up the energy that your voltage source supplies. Okay? That's one of your circuit elements. Okay? A radio, a TV, whatever. Okay? There's one thing they sort of left out here, and we'll talk about it a little bit later, but I'll go on and mention it now. You have to have a pathway. Okay? That, for electric circuits, are usually your wires. Okay? Can be some other things, but usually it's the wire. Now, here's where the problem came that I was mentioning to you. The current flow convention. Now, like I talked about before, when you have something moving because of potential energy, it goes from high potential to low potential. Drop the book from up here, it falls down there. When you have something moving because of heat difference, it goes from high temperature to low temperature. Always the upper potential, high potential to low potential. We saw that in the heat engine model that we looked at last time, the end of last class. If you had a concentration gradient, okay, it goes from high concentration to low concentration. Everything always moves down a gradient, whatever your potential difference is. Okay? So the current flow convention is that you go from regions of high potential to low potential through some type of external circuit, and that's usually your wiring or whatever it happens to be. They haven't address what the problem is. I've suggested it, but they haven't suggested it yet. We'll still get to it. I'll hang that out there for you to look forward to. Now, there is a water pump analogy that we make, okay? And that's not it. Well, I guess, okay. This is illustrating our structure of the electric circuit, okay? You have to have a voltage source. You have to have something provide the energy to make the flow happen. All right. Now, they don't specify here which is positive and negative terminal. We will a little bit later, okay? And that therein is the rub. So this is a voltage source, okay? Looks like a battery to me, and that is one type of voltage source. This maintains the potential in the circuit. Here is the part that I said they sort of left out here, the conducting wire, the pathway through which the current moves, okay? Here is your load, okay? That happens to be a light bulb in this case. It could be anything that's in your thing. The starter on your car, whatever it happens to be, that is your load. That's where the work is done. In other words, this provides the energy, that uses the energy, okay? And the circuit has to continue moving, so you still have to have conducting wire to go back to the other side of the battery. Now, conventional current flow convention, high potential to low potential, okay? That's how we normally refer to it, okay? Here's a water pump analogy. Now, analogies will work just so far. You can't take them forever, but you know, they do have pretty good. Here's your pump. What does the pump do? Pumps the water up to the upper reservoir. That gives the water greater potential energy. It's expending work to move the water up, okay? Then the water comes out of the upper reservoir, hits the water wheel, makes it turn, and gets on into the lower, and then picked up by the pump and go again. Now, what in our electrical circuit would be analogous to the pump? What gives the charge the energy?
Source.
The voltage source, the battery, whatever is doing that. So the pump corresponds to the battery or the voltage supply. Okay? What would the water wheel be likened to? Analogous to. Say again?
Load.
That would be the load, exactly. That would be the light bulb in the last example. What would the pipe be analogous to?
Current flow.
The what?
The flow.
Okay, the pipe, the water would be the flow. So water would be analogous to the charge, because that's what's moving in an electric circuit is the charge. What would the pipe be? It transmits the charge, allows the charge to move. The conducting wire, you have to have the pathway. And in the water wheel analogy, the pipe is the pathway. That's what takes it along. Now, like I said, all analogies will fall apart when you take them in too much detail. And here's where it would fall apart here. What if you broke the pipe here? What would happen? You're above the pump. Water would spill out, right? What happens in this, the electric current? What happens if you break the wire? Right, you won't get, it just stops. Everything stops. You don't spill charge out. You know, that's where it falls apart. Charge doesn't go spilling out somewhere. So that's one place the analogy sort of falls apart. But it was pretty good up to that point, right? Now, here's where the rub is, okay? The nature of the current. Historically, the nature of the electrical fluid, if you want to call it that, was unknown. We didn't know really what carried the charge, okay? Nowadays we do. generally what's carrying the charge? What is your charge carrier in an electric circuit? Well, we think of it that way anyway. Electrons. Okay? Remember, protons stay in the nucleus. They don't move around. So the only other charged particle is the electrons. Now, that's not always the case. There are other situations. I'll mention that in just a second. So generally, it's the electrons. The trouble is, what's the charge on an electron? Negative, exactly. So here is the rub, okay? In order for electrons to move, you have to go from the negative to the positive, because the electrons are repelled by the negative pole and attracted to the positive pole. So our electron current flows this way. But that's usually thought of going from low potential to high potential. The reason for that is electrons are negatively charged. They have to flow in the opposite direction. Now, I've heard it suggested that we need to blame that on Benjamin Franklin. That he fairly arbitrarily said, well, let's call this the negative charge and that one the positive charge, okay? You had to have two poles, a positive and a negative. He chose them one way, and it turned out making the flow go the other way. Conventional, you go from high potential to low potential, because you assume that either a chargeless or object is there moving, or a positive charge is moving. So that's your conventional circuit. Current goes from high potential to low potential, because that's what everything else does. High concentration to low concentration, high temperature to low temperature, high potential energy to low potential energy. Everything flows that way except electrons, because they're negative. And so they have to flow in the opposite direction. So, no one knew what they were before. They didn't know what it was, the electrical fluid. Benjamin Franklin supposedly said, well, let's make this pole the positive, that one the negative, say in one of the early batteries or something, because no one really knew what was moving. And that made it have to be electrons that flowed in the opposite direction. So, sorry about that, Ben. Okay. The current was thought to be a flow of positive charge until we found out generally it isn't. But you know, it really isn't. In a sense. In a sense it is, but in another sense it isn't. What's going on here or here? What's your current doing? It's alternating. It's not flowing anywhere, really. It's just going back and forth, back and forth, back and forth very, very quickly. What is really moving, you might say, is your field, the electric field. The actual charge carriers aren't important. Now, for those things where they are, like your automobile, what's your charge there? I mean, what kind of current do you have there? Direct current. So does that mean when I turn on my light switch, what you see is an electron racing from the switch to the light, through the battery, wherever it has to go. It's just going there really fast, because they come on almost instantaneously, right? Does that mean electrons move almost the speed of light? Nowhere close. Okay? In fact, the electron that's closest to that switch will probably not make it to the light for hours. Okay? Because that's really not what's happening. When you turn the switch, pull the switch, whatever you do to it, then the field is set up, and the field goes at almost the speed of light, not the actual charge carrier. And certainly an alternating current, that just go back and forth. You hit the switch there, I'm not sure an electron anywhere near that switch will ever make it to the light bulb. It's just the field is there immediately, almost immediately. Okay. So current is thought to be a positive flow, flow of positive charge, which would be your conventional current, but in reality, it's more complicated depending on the material. And here's why I say it's not always the electrons either. What's actually moving charge in your battery? Anyone know? There may be some electrons moving, and certainly electrons are involved, but what's happening in the battery, now if this is the good old lead sulfate battery, is that what they use these days or something more current? I don't know. But the old lead sulfate batteries, you have generally 6 plates in there, right? Okay? And each plate is, in the old days, was a lead plate, 6 pairs of plates. One was lead, the other was lead sulfate. And you had the fluid in there was, fairly concentrated sulfuric acid. It's somewhat diluted, but it's, let's say diluted sulfuric acid. Okay, so what's happening there, the lead ions are moving from left to right in this battery. The sulfate ions are moving right to left. There's not really that much electron activity. There is certainly some. And here is Shanika. Okay. What the electrons are doing are being transferred from the plate to the electrolyte. So that's all being done sort of behind. The actual movement of charge here is ionic movement of charge. Okay? Positive ions moving one way, negative ions moving the other way. Okay? So you have charges doing like this. Okay? And that's what sets up the potential difference. Generally, in a direct current, the electrons are flowing in this direction. The conventional current, we say, is going this way, but the electrons are actually flowing this way, but oh, so slowly. It's the field that goes almost immediately. Okay, we'll talk about that a little bit later, maybe. Okay. So, much more complicated. The opposite is correct. In metals, the current flow is actually the electron flow, which, because they're negatively charged, they go from negative to positive rather than positive to negative. All right. You'll see that again in the lab today, so hopefully you got it. Any questions on it? Okay. What are the actual current mechanisms then? Okay. Well, in liquids and gases, like the liquid in your battery, you generally have both positive and negative charges moving, but in opposite directions. Okay? In your metals, which they were talking about, what we have, and remember when we talked about heat and heat transfer and heat conductance, we said it's those free electrons that are moving things. Same thing, I'm sorry. Oh, man. In metals, it's those... Say again?
Allergy.
Possibly. I hope that's what it is. But like I said earlier, I had a treatment on Friday, and generally treatments sort of depress my immune system, so it could be I'm catching something, which I hope I'm not because I don't have much immune system to fight it. And one reason I was a little late at lunch today, I spent a fair amount of the morning trying to contact the people at this thing. They left a message and said I needed to come in for a shot to boost my immune system, but I couldn't this morning because I had an 8 o'clock class. I was trying to set up for tomorrow morning, and I couldn't get anyone that could do that for me. They were supposed to call back before 1, but they didn't make it, or may have been out of the office when they did. So still got to find out what's going on there. So hopefully it is allergies, but it could be worse. Okay. So in metals, these delocalized or free electrons are free to move throughout the metal. They're not really, this electron belongs to that atom. That's how it is in most things, like your sodium, chlorine, oxygen, hydrogen, anything. This electron belongs to this one, but it may be exchanged or shared with something else. But usually the electrons belong to certain atoms, not in metals. You have a whole bunch of electrons that we call free electrons. Some people call it an electron cloud. This book uses the term electron gas. It's neither a cloud nor gas, but it sort of gives that thing. They just move, and that's why metals are good conductors, because they've got a lot of these that are just free. You set up a field across them, they're going to take off and go. Okay? But I made it sound way too fast. The drift velocity of electrons is terrifyingly slow. Okay? Just really slow. Okay? Let's just assume. Now, this is not the best of the illustrations. If there's no field across this wire, really what you should have there are randomly but fairly equally spaced positive and negative charges. This makes it look like all the positives do here and all the negatives do there. That's not realistic. They would just be randomly there with the same number. But you apply an electric field, that would be going in this way, okay? Now that, remember what electric field was? The direction a small positive test charge would move if it were placed in the field. It would be going this way. Well, if the positive charges are going to tend to go that way, your typical electron is going to be moving in the opposite direction, because this would be the direction the positive charge would do, the electron would flow in this direction. Well, it might start up here and then be attracted to this ion, or positive charge here, but then once it gets there, then it's attracted to this one, to that one, to this one. Might even go almost backwards, not for very long or so, but it sort of wanders and meanders around. The term they use for that is a tortuous route, okay? So the electron drift, the slow drift component added by the electric field is it's dreadfully slow. The field almost is the speed of light. So what happens when you turn that switch, or the light switch in your car, okay, the field is set up instantly, okay, the battery's connected, the field's set up instantly, and electrons do begin to move, but they move really, really slowly, but the field is all through. So throughout the circuit, the electrons sense the field and start moving. So it's really the electrons right here that really enter the light or not. This is alternating. But the ones in your car, the ones really close to the light, they sense the field as soon as you do the switch to turn the light on, and then they start moving. These back here at the switch start moving too, but like I said, it can be hours before they get to the light bulb itself. It's the field is instantaneous, nearly the speed of light. The electrons, they just drift along and bump into things. They may hit another electron and bounce back, and then they pick up again. They're always trying to go down the field, the electric field, in the opposite direction, because they're negatively charged. Their drift velocity is incredibly, agonizingly slow. Field moves at nearly the speed of light. So that's what we sense, is the field, not the actual flow of charge. I think there's a good example coming up in the book. Yeah. And we'll get there, hopefully. All right. Yeah. Make sure I don't get ahead of myself here. A little more current details. Remember, in this chapter, little q stands for charge. Measured in what unit? No, joules is energy unit. A French physicist. Coulomb, exactly. Okay? Coulomb. And time is seconds. The time rate of change of the movement of charge, that's what current is. Remember from the very beginning, time rate of change of distance is speed. Time rate of change of displacement is velocity. Time rate of change of velocity is acceleration. Time rate of change of momentum is force. I mean, time rate of change of energy is power. I mean, we're all over the place using time rates of change. Time rate of change of charge is called a current. What unit do we use for current? You know this. What do you measure current in? No, that's potential difference. Surely y'all know this. No, watt is power. Okay. What do we measure current? Amps, yes, of course. Okay? So that is amp. Now, why they use a capital I to represent current, that's not standing for any one thing. These are parameters, but they do use capital I for current. The unit for current is amp, which is capital A-Y. Named after Louis Ampere, another French physicist. And remember, electricity was coming into its being about the time that France was at the height of its culture, okay? Around Louis the 14th, 15th, 16th, that time frame, just before Louis XVI lost his head, you know. But so there were a lot of great French physicists then. And by the way, if I'm not mistaken, Benjamin Franklin was an ambassador to France for some length of time. You can't convince me that he didn't get together with those French physicists and they talked shop a lot. That had nothing to do with governmental affairs, okay? So the time rate of change of current, coulombs per second, that's what an amp is. So the unit is, as you could have read from here, ampere, or we sort of shorten that to amp, capital A, named after Louis Ampere. Now, two types of current, we've already mentioned these. One is direct current. The charges move in one direction. Admittedly, they move awfully slowly, but they do move generally in one direction. And that's everything in your automobile, pretty much. And here's Coco. Oh, man. Okay. I know you're in here. There you are. All right. All right, so we're just missing Josh, Gary, Lauren, and Courtney. Okay, so hopefully some of them will be coming in. So in direct current, charges generally move in one direction. A lot of your electronic devices, your car, okay, believe it or not, is mostly an electronic device. Anything run by a battery, so a flashlight, things like that. Solar cells produce DC. That's one of the problems because our grid is AC, so any solar energy we collect, we have to convert to DC, which uses energy to do the conversion. That's one reason people like my brother who worked in the electric energy sector didn't really care for solar cells that much because you had to convert it to DC to get them to work well. And for the life of me, I mean, I'm naive about this, but when you see these huge power lines, you know, that go through carrying power from plants someplace to, you know, places that use electricity miles or even states away, and you know, they always keep those trees cut, grass mowed, you know, the towers are there, high energy going there. There's no shade. Why don't they have solar cells all up and down those towers? And that way you don't have to rely on something else. The sun would provide some of that. But they would also have to convert it to DC, AC to get it to work. Okay? So maybe that's why they don't do that. I don't know. But those are all DC. This computer, AC or DC? Well, I've got it plugged into the wall. I thought that was AC.
You're charging the battery.
Not quite, but close. You see this? That converts. DC, AC coming in, DC going out. Completely different kind of wiring, you know, here. This has to have wires going in two directions. You know, that's what do they call that? Dual wire or something like that. Here, there may be two wires, but you don't have to have them insulated away from each other the way that does. This converts the DC to AC. Yeah, that's running almost strictly, I would say strictly on DC. Whereas that you don't see the wiring here, that's AC, as are those lights and most of the rest of the room. Okay. So, what's happening with alternating current? those electrons aren't moving from here to there. They're just going back and forth and back and forth and back and forth. It's the field that's changing rapidly, but the field is set up immediately throughout the circuit, even though the charges aren't moving very far, and they certainly are not going far in the long run. They're just going back and forth and back and forth. There is no net current flow there. None. Absolutely no net current flow. Lots of movement of charge, but it's just back and forth and back and forth. That's alternating current. Okay? We usually use the same type units for both of them, but there are some subtle things that are a little different. We're not going to get into those in this course. Okay? Now, we're moving into electrical resistance. Okay. Before we get to electrical resistance, there is an illustration in the book that I think is worthwhile. And this is the figure 615. Electrons move very slowly in a direct current circuit, as in your car, in the computer, whatever, with a drift velocity of 0.01 centimeters per second. Okay? So if you go back to let me get my pen set up. This drift velocity is about approximately 0.01 centimeters per second. Okay? Now let's think about what a centimeter is. Centimeter is about the distance across your little fingernail. That's 1 centimeter. 0.1 centimeters would be about the thickness of a dime. Okay? That's a millimeter. 0.01 centimeters would say, take this dime, slice it into 10 equal slices. That's a hundredth of a centimeter. Okay? And that's how fast, in general, the drift velocity of electrons are. So if that's the case, let's say that you you step on the brake of your car. Okay? Now, if you're waiting for that electron, that when you step on your brake, complete a circuit, it starts sending electrons back to the brake light in the back, how long would it take to get there? They do the math here in your text with a distance of about 2 meters. That's from the brake pedal to the brake light, about 2 meters. That's about 6 feet, maybe a little bit more. That's 200 centimeters. 200 centimeters divided by 0.01 would be 20,000 seconds. Divide that by 60, divided by 60 again, and you're going to come out approximately 5 hours, more than 5 hours. 5.6 hours for if you waited for that electron to get back to the brake light, not going to do you a lot of good, is it? Okay, because you're already past the situation, miles down the road before the electron ever got there. But of course, that's not what's happening. It's the electric field. As soon as you step on that, the electric field now is throughout the whole circuit immediately, and electrons that were just before you got to the light, they start moving through the light, and that they give up their energy, and the light comes on almost instantly, almost at the speed of light. Not quite, but close. Doesn't take 5.6 hours. Okay. I did want to do that one because it related to cars before we got there. Okay. So let's now start electrical resistance. Okay. Now, the battery provides what to the current? Battery provides what? Voltage, okay? And voltage measures a couple or three answers would be perfectly fine, so it doesn't have to just be one. What is the voltage as a measure of? it's been so long, at least 15, 30, 20 minutes since we said this, okay? It was energy per charge. We call that the potential difference. Okay, that's what the battery provides. So you're providing energy to the charges. The electron is a charge, okay, is giving energy to it. Well, there's something in there that's using the energy. Now, we showed a light bulb before, but it's not just light bulbs. Even the wires have a little bit of what we call resistance. Electrical resistance is the loss of the electron current energy. Two possible sources, maybe more, but these are two that I'm going to mention here. One is collisions with other electrons in the current. Now, if you go back to the picture we had before of the electrons drifting along, they're being attracted by positive charges, which are nuclei, but they may bump into other electrons and be bounced backwards. So there's one form of resistance, okay, is other electrons that might be in their way, okay? Another is collisions with other charges in the material. Like those positive charges want to hang on to the electron and don't want them to keep moving. So either one of those would be places where those electrons lose their kinetic energy, the energy of motion, and slow down, okay? Now, there was a German physicist, came along a little bit after the French, probably, and his name was Georg. It looks like George, but I think they pronounce it Georg. Ohm, who came along and studied this resistance in different materials, and he came up with this law called Ohm's Law. So he came up with it. And later, people actually named this quantity he discussed, and you might say discovered, the resistance in a current in a circuit. They named it the Ohm. Named it after Georg Ohm, because he came up with this law, which they named Ohm's Law. And here's basically what he said. This may not be exactly like he said it, but the voltage that the battery or whatever provides to the circuit is proportional to the current that flows through the circuit. The greater the voltage, the more the current. Makes sense, right? What is that constant proportionality? That was the resistance. Now, some materials have higher resistance than others. You can also vary the resistance because of heat or other things like that, but that basically is Ohm's law. Voltage is equal to current times resistance. And this concept of resistance of the material of it in a circuit was called they named the unit for that ohms. Okay. Now remember I said this before. The parameter here is V for voltage, I for current, R for resistance. That's your parameters. The units for current is, we've forgotten already. Unit for current. Somewhere over here, remembered it. Unit for current. Oh, how long ago it was. Amps, okay? And we just talked about unit for resistance. What's the unit for voltage? This is the strange one. It's the word volt, okay? So the same thing we use as a parameter, we use as a unit. Very seldom will you see that happen. What represents the unit for a current, which is represented by the capital I, is amp, which is capital A. Okay. But the unit for voltage is volt also, and we use the same capital V for both of them. Now, since we named the unit for resistance an ohm, okay, what do you think symbol we'll use for that? Say again? I can't hear you. Okay, yeah, a voltage drop is voltage measured in volts. But resistance, we decided we're going to name it after Georg Ohm. So what unit should we use for resistance? What symbol? the name of the unit is an ohm. So what would you think we'd use? What letter to represent that? Well, you might say capital O, right? So give me some number of ohms. Make up a number. Any number.
6.
2, okay? So let's say we had 2 ohms. Is that a good choice of unit?
No.
Well, it's going to be an ohm, but yeah, O is not a good choice for the symbol. Why?
It looks like a 0.
It looks like 20, and you can't tell, are you talking about 20-somethings, or is that 2 ohms? Yeah, so a little confusing, okay? Well, what else can we use? I already used H's for Henrys and HZ for Hertz, so those have been used up. You don't use for meters and lots of other things, so it won't go there. So I actually went to a new alphabet, okay? The Greek alphabet, the Greeks were known for their science and wisdom, Aristotle, those kind of people. In the Greek alphabet, the letter for, capital letter for, that represents O, is Omicron. And that looks just like an O also. So we can't use that one. But the Greek alphabet, surprisingly, has 2 letters that, when you spell them out, they start with the letter O. What's the second? Omicron is one. Its symbol is O. What's the other one? Anyone ever heard of the alpha and the omega? Okay. What that means, alpha is the first letter in the Greek alphabet. Omega is the last letter. They don't have a Z in the Greek alphabet. They have a letter we don't have any correspondence to, and it's omega. So when they say first to last, alpha, omega, that's where that phrase comes from. But it starts with the letter O, so that's the one we use. And the symbol for omega, capital symbol for omega, is sure enough that. That is a capital omega, and that represents ohm. That's the one we use to represent ohms. One of the few Greek letters we use to represent an object. We do have a few others, like a micro, a millionth of something. We use a mu, okay, a lowercase mu. Now we use, not as a unit, but we use the lowercase omega, which doesn't look at all like an uppercase omega, when we're talking about angular frequency. And that happens to be, it looks like a W with no serifs on it, just that symbol. This is lowercase omega. That's not the one we use. We use uppercase because it's named after somebody. So even in the Greek alphabet, we use the capital omega. Now, let me cover this before I go into this. Anytime you have an equation like that, you can come up with 2 more equations. And you think of 2 more that are completely equivalent to that. I is equal to V over R, perfect. And R is equal to V over I. You just divide them differently, okay? So all 3 forms of that are forms of Ohm's law, depending on what you're looking for and what you're given. So this shows one of them, I is equal to V over R. And this says that current is directly proportional to voltage, which we saw here too, but it's inversely proportional to the resistance. Meaning the greater the resistance, the less your current, the less resistance, the greater the current, right? They're inversely proportional. The greater the voltage, the greater the current, the less the voltage, the less the current. Those are direct proportions, okay? Now, let's go back to the omega. Just to talk about how totally weird physicists are, or can be, okay? There is another thing that we like to measure, okay, when it comes to electricity. Whereas resistance is that loss of current energy, the things that impedes the flow. There's something else called conductance. How easily does something flow, okay, electrically, okay? And that unit is called, let's not get into what it's called yet, but it's called, the term is conductance. It is exactly the reciprocal of resistance. So if you had a resistance of, what did y'all say a resistance of? 2 2 ohms, the conductance of that material would be 1/2 of whatever unit that is. So what are we going to name this new quantity that represents conductance? We need a name for it. I don't know who came up with it, so I don't know how to name it that way. What will we name this new unit, the unit for conductance? We need a name for it. Any ideas?
Alpha.
Okay, sounds good, but they didn't. They chose the name mho. Now, where did they get the term mho? It wasn't that Larry and Curly's friend discovered it. That wasn't it. Okay. So where did they get the term mho to talk about conductance? Maybe it would help if I spelled it for you. A mho is a MHO. Where did they come up with that term for conductance? Any idea? Frederick Moe came up with? Nah, that wasn't it. Where did they come up with that unit name?
That's an abbreviation or something.
Say again?
Is that an abbreviation?
I can't.
Is that an abbreviation or something?
No, not quite. It's exactly the reciprocal of an ohm.
It's old back.
It's ohm spelled backwards. That is a square how they came up with the unit of conductance. They just spelled ohm backwards. So what unit are they going to use for that? They can't use an M, that stands for meter. I don't think MH would make any sense. So what unit are they going to use to represent a mho? Nope. Close. Because it's a reciprocal, they just flip an omega upside down. That's not any symbol in the world. That's not in anybody's alphabet anywhere. They just reciprocated or flipped it upside down. That's the symbol for a mho. I'm not making this up. The physicists are sort of strange. Okay. All right. So there's Ohm's law. This actually is going to be Thursday's lab, Ohm's law. So you got 2 pretty good labs coming up. You might enjoy Thursdays even more than today's. All right, let's look at a little bit more about resistance. Okay? There's several factors that enter into resistance of a material, okay, of an object. The first is the type of material. And this is not unlike what we saw in heat resistance, because in heat resistance, the metals transmit heat very easily with very little resistance. There are ceramics and other things like that offer a lot of resistance. That's why we call them insulators. Well, the same thing here. There's different materials have different what we call resistivities. And believe it or not, very similar to what we found with heat. The best conductors of electricity with the lowest resistance are your metals. Guess which one is the best? Silver, just like it was with heat. Next best, we did this last time, didn't we? Copper. Okay? So, and really the difference between silver and copper is pretty small. Copper is just a little bit more resistant than silver. But why don't we use silver?
Can't bend it.
Second?
Can't bend it.
Yeah, you can't bend it, and it's also very, very, very expensive. Okay, copper is much cheaper. So yeah, copper is ductile, and you can make it into wires. It does really nicely. Silver wood. So the type of material. Next after that, well, I don't know if it's absolutely next, but one of the next ones is, well, gold is in there somewhere, but then aluminum. The next cheap metal is aluminum. But aluminum has a lot more resistance than copper does. Now that leads to another issue. Back in World War II, when we were fighting the Germans and later the Japanese, and I mean, pretty much into what at that time was called modern warfare. No more trench warfare where you dug trenches and armies stayed within sight of each other and fired at each other in the trenches, and more people died in the trenches because of disease than they did from getting shot. You know, it's just a really nasty, ugly war, World War I. World War II, the Germans came out with this concept of blitzkrieg. I don't know if you remember that. They just went in with heavy armament, heavy everything, and just blasted thing, and using a lot of artillery and used aircraft, and we did too, and dropping bombs and firing things. Well, suddenly we were letting our weapons do more of the fighting than we did, which sounds good to me. I mean, I'd rather weapons get expended than me get expended, okay? Well, anyone know what the shell casings are, whether you're talking about bullets or projectiles of any nature? What are your shell? And by the way, cannonballs were out of the picture now. That was previous wars. Now we had projectiles, and you had this sleeve, and you didn't have to pack the dynamite or whatever your explosive was there and then put the ball in. They came pre-packaged. So you had to have a shell that contained the explosive, and then the projectile when the explosive went off, it took off, and you didn't have to pack between every time. As fast as you could feed the bullet in or the projectile in, you could fire it. Okay? So you had to have this sleeve. Does anyone know what the sleeve was made of? Brass. And anyone know what brass is? You won't find it on the periodic table. It is a metal, but it's not an element. It's what we call an alloy. And brass is an alloy. I'm trying to remember what the second metal is. I think it may be zinc, but the primary one is copper. So all of a sudden, we were building ships and planes and everything that needed lots of complicated wiring, and we were manufacturing tons and tons and tons of ammunition, all of which needed brass. Now, why do we use brass as a shell casing? One reason, this may not be the only reason, but one reason is that brass does not conduct electricity. Well, I don't want to say that. Yeah, that's pretty much it. It doesn't arc and spark. And if you have concentrated propellant in it, you don't want it picking up any random sparks and just blowing up on its own. So they use brass because of that. Okay? So, guess what? Copper went in very short supply. All the copper they could get their hands on and mine and everything else they were using to build munitions. Bullets, casing, shell casings, wiring for aircraft, airplanes, ships, everything. High demand of copper. So houses that were being built, or that many, but houses were being built, copper was very expensive, and they didn't even want you using it because they wanted that for the war effort. Okay? So what did they use? I had to go down the list. Gold was too expensive. The next metal down there was aluminum. No, silver was way too expensive. It was even better than copper. So they went down to aluminum. Yeah, aluminum would work. It didn't have as good of resistance as copper. It had much higher resistance than copper. So a lot of World War II houses were built with copper wiring. These don't exist much anymore. Why not?
They burned down.
They burned down, exactly, because over time we started using more and more, making more and more demands on our electrical systems. Because back then, it's the lights was all you used electricity for. But then they got to using washing machines and irons and air conditioning systems and stuff. But after a while, you put way too much load on that aluminum wiring. It got too hot. The houses burned down. Or they retrofitted and put copper wiring in rather than aluminum wiring. One of those happened, so the type of material is important. It affects the resistance. And aluminum had worse resistance than copper did. Another is the length of the wire. The longer the wire, the greater the resistance. That sort of makes sense, doesn't it? Let's go back to the water analogy. Okay? I don't know if you've ever run into this before, but if you have a hose, water hose, and you string it out there and you're watering something, but then you want to water something further on and connect another hose to it. So now you're 100 feet away watering, and then maybe another one. After a while, there's not much water coming out, okay? The same amount of water maybe, but the pressure is much less. Why? Because of resistance in the length of the hose, okay? Same thing here. The longer the wire, the greater the resistance. The type of material, the greater resistance. The longer the wire, the greater the resistance. Another one, the cross-sectional area. Now that makes sense, doesn't it? A big pipe, lots of water can go through it. A small pipe, less water goes through it. And you have more resistance per unit because most of the area is free from resistance. It's the pipe that gives you the resistance. The water passing past the pipe. And the smaller the pipe is, you have more water touching the sides per unit than you have here. Most of this is in the middle. So the cross-sectional area is important too. Okay? And then the fourth one is temperature. The higher the temperature, the greater the resistance. Because your molecules are bumping along each other more rapidly, so sure enough, the temperature, the higher the temperature, the more resistance. Because the more likely the electrons are to get banged around. All right. Do y'all remember what a incandescent light bulb was look like? In a few years, not that many people are going to remember what incandescent light bulbs were. Because recently they went to CFLs, compact fluorescent lights, rather than those others, and now they don't even use those much. What do we use now? LEDs, okay? Because they're much more energy efficient. Well, let's think about that incandescent bulb that had a little filament. Sometimes if it's a clear light, you can see that little filament in there. Let's think about, anyone know what type of material they use as a filament? Not copper. If they use copper, it's going to transmit electricity really easily. It's not going to heat up and get light, okay? Defeats the purpose. Anyone know what material they typically use? Tungsten. Way down the list. Much more resistance than tungsten. Therefore, with the higher resistance, it gets hot, and when it gets hot, it glows. And it glows a whitish light. That's why they use tungsten. Now, did any of you ever look at those filaments in those bulbs? You know, especially those clear ones you can see through. What did you notice about those filaments? Anything? They look like little springs, don't they? They're little spirals, okay? Well, think about that. What if you stretch that out and make it like this? You got a pretty long filament there. So again, they use the length of the filament. The greater the length, the greater the resistance. The hotter it gets, the more it glows. How about the next one? What did you also notice about the filament? Great big old wire? No. They're about the, if I had some, about the thickness of a hair. They're very, very small cross-sectional area. So the smaller the cross-sectional area, the greater the resistance. The greater the resistance, the more the heat. The more it heats, the more it glows, better light. Okay? Now, have any of you ever noticed when is the most likely time for a light bulb to blow out? I'm talking about incandescent. When do you remember seeing light bulbs go out? As soon as you turned it on. Now, why would that be? Well, when you turn it on, the light bulb's probably cold, right? And if it's cold, it's conducting more electricity. The more electricity, the more resistance. The more resistance, that's when a weak filament that's been used a lot is going to go down. When it was hot, okay, it had more resistance, so less currents flowing through it, so it's not likely to blow. But when you first turn it in from cold, that's going to do it. So you see, every one of these is reflected in an incandescent light bulb. Okay? So the cross-sectional area, the length, the temperature, I don't know why they pointed there, the material. Okay? All those contribute to the resistance factors. All right? Now, there are some strange materials that have almost no resistance at all. And when I say strange, it's because they're very rare, but also, who can explain why? I don't know that anyone has. In fact, I haven't done research on this, so I don't know. But just looking at lists of Nobel Prize laureates in physics, it seems like to me superconductors have more than their fair share, okay? Because the very first superconductor ever discovered, that guy surely got a Nobel Prize. But that one was a very, like I said, rare. Now here's what it requires to be a good superconductor. It doesn't have to be a good conductor up here. In fact, some things that are really lousy conductors at normal temperatures, when you drop the temperatures to very low temperatures, suddenly they become superconductors. Copper, when you drop it to low temperatures, it doesn't really become that better of a conductor, okay? It does get a little bit because temperature helps you conduct better, but it doesn't follow that the same type around. It's some of your oxides, and other things that make these superconductors. And those usually aren't good conductors to begin with. But when you get them cold enough, suddenly they become good superconductors. The very earliest ones discovered, I think, were down around just a few degrees Kelvin. A few K. You don't use degrees of Kelvin. Really close to absolute zero. Those were hard to deal with because you had to have them such low temperatures. So anything you picked up in loss of resistance, you lost all that because you had to get the temperature so low. Okay, so it wasn't very energy conservative. Okay, but then the next round, they found superconductors at when I say much higher temperatures, from a few degrees to a few teens of degrees. Okay, 15 to 18 degrees rather than 3 or 4 degrees. Okay. And then they got some up to maybe 30-some degrees K. I keep saying degrees. 30-some K. Wow, that's a great improvement. Because in order to get down to a few K, just a few, like 3 or 4 or 5, you have to use liquid hydrogen or liquid helium. Really cold stuff. When you get up to the 30s or 40s K, now you can use liquid nitrogen. It's a lot easier to deal with liquid nitrogen. It's not nearly as cold for one thing, but you can use that. So they have got some really much better, and every time they got a new family of them, that guy would usually win, or that team would win the Nobel Prize in a few years. Okay. Now, I can't tell you why they work, we just know they do. Now, what it means to be a superconductor, once you get a current moving in it, you can remove the voltage source, and the current keeps flowing basically forever, because there's no resistance to make it stop. That's a pretty nice thing to have, isn't it? Now, have any of you heard, I can't remember the name of it, the very fast trains they use in Japan? They are extraordinarily fast. Hundreds of miles an hour trains. And you think, how in the world do they do that? Well, they use superconductors. Because a superconductor, because the current can flow continuously in it without adding any power, anytime you have the movement of current, movement of charge, you induce a magnetic field. So superconductors can make very strong magnetic fields. And if you have a strong enough magnetic field, you can actually elevate the train off the track. And that's what they do. They have superconductors in the track, carrying the charge, making the very strong magnetic field, and it actually repels the thing, so you have no contact between the wheel or whatever you have there, the rail and the track. None. So you have no resistance there. So they can go very, very, very fast. Japanese have perfected that. I don't know. It seems like a few other countries have tried to copy it, but the Japanese were the first and I think the best at doing that. I wish we put more emphasis onto that kind of stuff than we do, but we just typically do not. Okay. By the way, let me just hit a few other things here. There's a mistakes and misunderstanding on page 151 on what is electricity. That's a very good question. Even people who work with electricity just about every day don't really understand fully what it is, so I'll just let that go. Before we get into electrical power and work, let's go back and do examples 6.3 and 6.4. I wish I had someplace that they gave me some white space. Here's some. So let's do example 6.3. This is on page 152. A light bulb, okay, in a 120 volt circuit. 120 volts. What's that a measure of? Almost sounds like a trick question. Voltage, okay? This is the one that the parameter and the unit are the same, V, okay? They stand for different things, but they are the same letters, capital V. So 120 volt circuit. Now what does that tell you? When I say 120 volt circuit, you should immediately come to mind what kind of circuit we're talking about. What two kinds of circuit do we have?
AC.
Say again? AC and DC. Which is that?
AC.
That's going to have to be AC. You do not have 120 volt DC circuits. If you do, you got some frying wires going on. I mean, they're glowing. They're so hot if you got that much voltage in a DC circuit. So this is AC circuit. Doesn't matter in the problem. I just wanted you to realize that. Okay? It's switched on and a current of 0.50 amps. 0.50 amps. Okay? There is your current. What symbol do we use for current? Say again?
C.
C, you said? No, it's not. Say again? I, you got it. Capital I. That's what we use for current. That's a parameter. Okay? A is the unit, and that's amperes. Okay? Flows through the filament. What is the resistance of the bulb? So we're looking for the resistance of the bulb. How are we going to determine that?
Formula.
Which one?
R equals V over I.
Okay, very good. Whose formula is that?
Ohms.
Ohm's law in one of its many forms. So we take your 120 volts and divide it by I, which is 0.50 amps. And what do we get? 240 watt units. What unit do we use for resistance?
Omega.
Omega is the symbol. What's the name of the unit? Ohm. Okay, yeah. 240 ohms. That's your resistance of that bulb. Okay. And by the way, 0.5 is pretty good sized current, so most of the time we have resistance greater than that. Okay, and they got 240 ohms too, good for them. Let's do 6.4. What current? So this time we're looking for what?
Amps.
Amps. What's the symbol?
A.
Yeah, but yeah, the symbol for okay, yeah. The parameter is I. So this is the unknown in this problem. What current would flow through an electrical device in a circuit with a potential difference? So your potential difference, what do we usually use symbol for that? Potential difference. What symbol?
Resistance.
No, potential difference. Volts. The V is 120 volts, just like before. So again, probably AC, almost certainly AC. And a resistance, that would be R, is equal to 30 ohms. Okay. Now just looking at these two problems, would you expect this current to be more or less than that current? That current you had, that circuit you had 240 ohms, now you only have 30. You have the same voltage, Yeah, your current's going to be a whole lot more because the resistance is less. Inverse relationship. You're absolutely right. So what would it be? Second, yes. That would be V over R, just reversing the last one, I's and R's, and that would be 120 volts divided by 30 ohms. What's a volt divided by an ohm? Here, by the way, the zeros go out. 3 will go into that 4. 4 what? I is measured in what units? You said it earlier. Amps. Ohms is resistance. That's 4.0 amp. In fact, the book just called it 4 amps. I don't know why, but I guess the 30 may not have been two significant digits. They just say 4 amps. It doesn't matter. Okay, 4 amps. A lot more current. In fact, 8 times the amount of current, and that's not surprising that the resistance was 8 times less resistance here. Those are direct proportions. Okay. So, 2 examples of Ohm's law applications. Y'all are pretty familiar with these, right? Some of you. Okay. All right. Let's go on back to electrical power, and electrical work. Now, how are those 2 terms related to each other, power and work? Are they at all related? How? A couple ways you can answer that. Pick one. How are work and power related? Are they the same thing? Not quite the same thing, but they are related. How? Say again? I couldn't hear. No. The same units are embedded in one to the other, but they're not the same units. Otherwise, they'd be equivalent. If you're talking about work and energy, yes, those are equivalent. They use the same energy. What unit do we use for work and energy? Since you brought up units, what unit do we use for work or energy? Same one. I don't have one on here, but Joule, exactly. Okay, what do we use for power? What unit do we use for power? What unit? What unit? Watt, yes, you got it, okay. A watt. And how is a watt and a joule related? We've already talked about it before. You did it in lab, except you use horsepower, but what related work to energy? Time. How are they related? I've already said it at least once today. Power is the time rate of change of expending energy or doing work. That's what power is. So a watt is a joule per second. Okay? Helpful to get these things straight because they help you in working problems. Okay, 3 circuit elements contribute to the work done by a circuit. Of course, voltage source. What does a voltage source do?
Supply voltage.
Apply voltage, very good, okay. And what is a volt? Anyone remember? It's been at least 30 or 40 minutes, so I can easily see how we could forget it. What is voltage? Voltage source, potential difference. Energy per charge, remember? Joules per coulomb, that's what a volt is, a joule per coulomb. So, how does it contribute to work? Work is measured in joules. The voltage source provides the joules, provides the energy that contributes to doing work. Absolutely essential. Okay, the electrical device, how does that contribute to the work? That could be the light bulb, the computer, the space heater, whatever. Motor on your car, the starting motor, what does it do? How does it contribute to the work?
It's what's using the power.
It's what uses the power, uses the energy. The voltage source supplies it, the electrical device uses it. So that's how it contributes. It's the one that does the work, uses the energy that the voltage source supplies. And then, third, and we talked about these three before, the conducting wires, what do they do? Voltage is joules per coulomb. You got to provide a pathway for those coulombs, the current, to get to the electrical device. That's what the conducting wires. They maintain the potential difference across the device. Now, part of what that means is the conducting wires, you hope, are not using much power. They do have a little bit of power loss because they have finite length and diameters and everything else, and they don't have perfect conductance, but they do. But they generally not going to do. They maintain the potential difference across the device because you've got to get the charge and the field from the voltage source to the device. Okay? The input wire is at the higher potential than the output wire, at least in a conventional current. Okay? The output wire is often called the ground in AC circuits. I hear y'all talk about that a lot. Y'all used to call it the ground? Yeah. Yeah. And AC circuits, so y'all are dealing mostly with DC circuits, but use the same type idea. There's no potential difference. If there's no potential difference, in other words, no voltage source, you have no current. Okay? And then this is a weird thing to put here, but they put it there. What in the world are they meaning by that? What do we think of those lines that are outside? We think of them as fairly high voltage power lines, right? Because when they get to your house or near your house, you have, and we're going to talk about this later, maybe next time, we have step-down transformers that drop the voltage and increase the current. And we'll talk about that later. Okay? So therefore, these wires, pretty high voltage. And yet you see birds perching on them. Why aren't they fried?
They're not grounded.
They're not grounded. There is no pathway to get from them to ground. They're just up there on the wire, so they're not. So the bird on the wire has no potential difference. See, that's the same potential the wire is. There's no difference there. Link to ground, yep, fried. Okay. Sort of a dumb example of that. When we lived in the first house we bought in Birmingham, we had rented a place for 1 year, and then we bought a place the second year. And shortly after we bought the place, we got a dog. And she was a headstrong little puppy, and throughout her life was. She didn't particularly like to be in the backyard, which is where we kept her while we were at work and my wife at school. We kept her in the backyard. She didn't like being a backyard dog. She couldn't see what was going on back there. Okay, so she was able to get out of whatever we did. A chain link fence, really, she would find a way out. Okay, and I tried all sorts of things. I ran barbed wire around the basis of that, so trying to keep her. She still got under it. Didn't bother her. She might get scratched a little. She wanted out. Okay, and actually, early on, she in no time learned to. I had one of those things that go like this on the pole. She learned she could pop that open and get out. So at first she used a gate like any decent dog would do. Unbelievable that she did it. And so I put a bicycle lock through it. I didn't lock it, but I put it. She couldn't get that open. So she started going under the fence. Okay. I put barbed wire. That didn't work. I tried everything. I put concrete blocks. I put everything I could think of, and she would find a way out. Okay? And finally, our neighbor on the backside, he was laughing at us as we did this. He said, the only way you're going to stop her is put an electric fence there. He said, it's not going to hurt her, but she'll touch it once, she'll never go back again. In fact, you can turn the power off. Once she's been shocked a few times, when she sees that, she's not going to go close to it. Put it down near the ground, so she'll have to hit it when she's trying to get out. So I did it, and sure enough, it tended to work until I took his advice and turned it off. As soon as I turned it off, she was out again. And we didn't quite figure out what was going on there, except I did notice sometimes she would get close, sort of like she was listening to see if she could hear, and it wasn't making any noise. I don't even think the dog ears. And then we figured out what she was doing. She was getting her whisker close to it, and when she felt the tingle, she was back going off. Way too clever of a dog. Okay? But she found another way to check it too, and it didn't bother her whiskers as much. If I was out working in the yard, she'd come up to me like the dear dog she was and push me into the fence. If I jumped, she knew it was on. And she did that more than once. I'm ashamed to say. She was way too clever of a dog. But anyway, we had to leave the electric fence on all the time, basically. And one day I came home, and there was a squirrel like this, squirrels run on power lines all the time, and this had almost no electricity in it, but it was just enough that the squirrel, for some reason, grabbed the wire while it was standing on the ground. Enough, just a very little amount, but it did kill the squirrel. And I had to haul it off. She would have taken it herself, but she got shocked every time she tried. Okay. So anyway, as long as the bird is not connected to the ground, it's at the same potential as the wire. Now, this is what makes, when you have storms, and if, say, it were to happen that you're out in the storm driving in your car and the tree falls over and knocks down the power line and it breaks across your car, and you don't notice a thing, you don't get a shock or anything else, is it safe to get out of the car? No. Why not? Because when you're in the car, you're on rubber wheels and you're not grounded. As soon as you step out, this foot in the car, this foot on the ground, zip, okay, you're dead. Okay. So it's not a good idea ever to get out of a car at power, or to do anything with down power lines. They may look perfectly harmless there. Don't touch them, because you may provide the pathway for ground. You may be the conducting wire, and that's not a good thing to do. And what happened to the squirrel is the same thing that would happen to us. That wasn't enough charge in that wire really to kill a squirrel, except, and this actually happened at our high school. Every year in the fall, the fair would come to town, and it was a cheap little deal, but because we were in a small town, it wasn't like the state fair or something like that. And these guys would come in and set up all the wires going everywhere, running around to run the shows and the lights and everything, and all the rides and stuff. And they must have had a short somewhere, because Gary's here. Cat Thompson, a guy in my older brother's class, he passed by underneath between two things. You probably shouldn't have been back there, but we're going through. And he just reached up to step across something and didn't realize this was a hot wire. He reached up. And as soon as he reached it, his muscles froze. And he was about to be electrocuted. And Phil Chalker, who was not known to be the brightest bulb on the array, he found a bat or stick or something and hit Tat's arm away. Otherwise, Tat probably would have been electrocuted. But he did it real quickly, knocked his arm away. Actually broke his arm, but Tat was okay with that. He'd rather have a broken arm than be electrocuted. But you see, he couldn't release his hand because his muscles closed over it, and that's the same thing that happened to the squirrel. Electricity will do that to you. Very little current or other things, but it was just enough that the squirrel couldn't release and died trying. Okay. So let's look at power in circuits. Power meaning what? Oh, it's been a long time this time. What is power? Oh my goodness. What is power? Okay, you may have said the units. Oh, you didn't. Okay. What is power? What's the unit for power?
Volts. Is it the time rate of change of work?
Time rate of change of doing work, exactly. That's what power is. And what's the measure for work or energy? Joules, time, joules per second. That's the what? No, a volt is a joule per coulomb, energy per charge. Okay? What is a unit? Watt, exactly. Okay. So power in circuits is the time rate of using thing, and surprisingly here is another formula. Multiplication, which you can come up with two more, that would be division problem. Power is equal to current times voltage. Now why would that be the case? Someone remind me what current is. Yeah, it's measured in amps. What is that a measure of? Current. We talked about it earlier today. In fact, you gave me the unit for one of the components. I'm pretty sure. Current is the time rate of moving charge. So that's a coulomb per second. That's what current is. Okay? And what is voltage?
Volts.
Yeah, it's measured in volts. And what is a volt? What does voltage measure? Potential difference. What does that measure? We've only done it 2 or 3 times today, but it's been a while. Voltage is, in fact, I just said it because someone, joules per coulomb, you got it. So a volt is a joule per coulomb. Now notice what happens there. The coulombs cancel out, and what are you left with? Joules per second, which is a measure of power. In what unit is a joule per second? What unit? Watt. That is a watt. A joule per second is a watt, and that's what we use to measure power. Why is it a capital W? James Watt. Okay. He did a lot of the. He defined what a horsepower was, and then they named the electrical power after him. So yeah, that's exactly it. Power is current times voltage. Okay. Now with that in mind, give me 2 other formulas you can get out of that one. 2 other formulas. I is equal to, say that again? P over V, perfect. Or V is equal to P over I. Perfect. Perfect. Okay? So we see here that power is directly related to the current at constant voltage, or directly related to voltage at constant current. Okay? Here you see that current is directly proportional to the power, but inversely proportional to the voltage. And here we see voltage is directly proportional to power, just like we saw here, but inversely proportional to current, we saw there too. So yeah, there are all the different forms of this. It's a lot like Ohm's law, but it has different things that you're dealing with. Now, you can combine it with Ohm's law to come up with lots of other interesting combinations. So we might do that in a minute. In fact, let's go on and do it now. In Ohm's law, what is voltage? Ohm's law. Oh, it's been a long time.
Current times times resistance.
Current times resistance. Whoa, what are you doing here? Okay. Current times resistance. So instead of voltage here, we're going to say current I times R, which is I squared R. Look at that. Power is related to the current squared. So anything that uses a lot of current is going to use a whole lot of power, because you're going to square that current. If it's a big current, square that, it gets even bigger. And then whatever your resistance is, that multiplies by it. So think of this. And here's something good to keep in mind. Anything that produces a lot of heat is using a lot of power. Well, is using a lot of current. That's what produces the heat. So irons, air conditioning systems, ovens, ranges, clothes dryers, those are the, hey, keep them coming. Finally going to get a good crowd here. Actually, we've got a good crowd, but a better crowd. Okay, right now, all we're missing is Josh and Lauren, I think. Good deal. Okay. All right. So, anything that produces a lot of heat is going to make that power bill go up really fast. Okay? And my younger brother works for the power company. He used to like to stand out and look at the meter, and when that AC kicked on, which is what kicks on is the compressor, which is compressing a gas, producing a lot of heat. You watch that. You can see it start doing. Turn on the clothes dryer, there it goes. Turn on the oven, heat, there it goes. You can watch that and it would speed up noticeably. Okay? Now another way you could express this is, instead of, let's solve this for I, Ohm's law for I. What would that be? I is equal to V over R. Exactly. Okay? So if you put that in for the I, you have P is equal to V over R times V, right? Which will be V squared over R. Okay? And again, you use a lot of voltage, you're squaring that, you're producing, you're increasing your power usage. Okay? But this time you're dividing by R, so that tends to reduce it, because usually things have pretty high resistance. Over there you're multiplying by R. So actually the more current, greater heat, then that's going to increase your power consumption faster than doubling the voltage. So that's still going to do a lot. All right, so let's now get to, why do they have electric bills here? What are you paying for when you pay your electric bill? Have you ever noticed? What would you say you're paying for? What do most people call the bill?
Power bill.
The power bill. Are you paying for power? No. You're paying for energy, not power. Power is rate of doing energy. What you're paying for in your electric bill is the actual energy used. Now, have any of you ever paid close attention to what units you're paying for on your power bill? Any of you? Some of you don't even see the power bill. Mom or Dad pays it, huh? Okay, or someone pays it, right? That's good news. But guess what? One of these days, you're going to be paying it, okay? So, anyone ever notice what's on the bill? It's not kilowatts. It's actually the term kilowatt hours. Kilowatt hours, okay? Someone remind me what a watt is, what power is. We've said it several times today. Power is?
Time rate of change of work.
Yes, work per unit time. Absolutely. What if we multiplied both sides of the equation by time? You lose time here and you get work. Now that's not watts, that's work. Okay? Work is equal to power times time. Okay? And guess what? Power is measured in watts, and time, one way of measuring time is hours. multiply power times time, you get the work or the energy used. That's what you're paying for in your electric bill, not power. It's not a power. Even though Alabama Power sends you the bill, you're paying for the electrical energy you use. Okay? So it's the energy you're paying for. So let me erase at least some of this so we'll have room to see what comes next. Okay, I thought I hit it, but I didn't. Okay, now. Okay. All right. So, what you're paying for, what you're paying out of pocket, the cost, the dollars you pay, is the power times the time. Okay, energy is power times time, just like we saw down here. Energy is power times time. Times the rate, how many dollars per kilowatt hours. Okay, and then they changed this from kilowatts to watts to watts to kilowatt. So why do that? Change the watts to kilowatt to begin with, so you don't have to do this. Okay, and you do the rate. Now I can remember not that many years ago when Alabama Power used to advertise and brag on for as low as 3 cents per kilowatt hour. I remember when they advertised that. Nowadays, nowhere close to that. I remember when it went past 7 cents, that was more than twice what they were advertising way back. And now I bet you it's in the upper teens or lower 20s per kilowatt hour. Okay? Now you might ask yourself, if you're really paying for energy, why don't they use the unit for energy? What's the normal unit for energy? Joule. Okay? Remember, a joule is a very small amount of energy. 1 kilowatt hour is about, I'm just doing off the top of my head, something like 3.9 million joules. Something like that. Do you think Alabama Power wants you looking and see how much energy you use and it's in millions of units? I think not. So they use kilowatt hour. Kilowatts, so that's 1,000 watts in an hour, not in a minute or a second, because usually we do joules per second. No, not even that. Hours. So it makes a much slower number because it's a huge unit. Okay. So yeah, that's why they don't use joules or even kilojoules. It would be an enormous number of people. Hey, we've got to cut back on it. And, you know, they don't want you doing that necessarily. Maybe on some summer days they do. All right. So that was almost the end of electricity. Let's see if we can go back and do some problems. Don't think no. All right, let's do them here. 6.5, 6.6, and 6.7, and 6.8. Okay, 6.5. Oh, and by the way, I was looking for this before, and finally I see where it is now. Another handy conversion factor to remember is that 746 watts is equivalent to 1 horsepower. Okay? So a watt is a very small amount of energy, of power. A horsepower is a pretty decent size. A kilowatt, though, is even bigger than a horsepower, but they're close. 0.746 kilowatts is 1 horsepower. So a kilowatt's bigger than a horsepower, but they're pretty close. 3/4 of a kilowatt makes 1 horsepower. So they're really close to each other. Okay, so let's do example 6.5. A 1,100 watt hair dryer. 1,100 watt hair dryer. What's that a measure of? Power, that's your power usage, okay? The rate at which you're using energy, okay? Is designed to operate on a 120 volt circuit. What's that a measure of? This is the easy one. Volt, the potential difference in volts, okay? How much current does a hair dryer require? What are we looking for? I. The current is measured in I. That's the unknown here. So what's going to relate those together? I is equal to P over V, perfect. Okay? And that would be 1,100 watts divided by 120 volts. I think you're going to have to use a calculator on this one. I can't do that one in my head. I could get rid of 1 0, but that doesn't help a lot. 110 divided by 12 will be just a little over 9, right? How much? Anyone got a calculator? You're going to be working on today's test later with no calculator. Interesting. Okay. Just a little bit greater than 9. At least that's what I get. What's the next digit?
6.
Okay, round that up and make it 9.2. 9.2, what unit for current? Amps. Very good. Okay, and there you have it. That's what the book got as well. Okay, an electric fan is designed to draw 0.5 amps. What's that a measure of? What symbol for that? I, capital I. Good. Okay. In a 120 volt circuit, what's that a measure of? That's volts, which is potential difference. Okay. Joules per coulomb, by the way. Okay. What is the power rating of the fan? So what are we looking for? Power. Okay. And what's the formula for power? That's your unknown here. I times V. I times V. Now, in the old days, this is a little bit of a digression here. We used to use, instead of voltage, we would use, the parameter would be E, so you wouldn't be confusing the parameter with the unit, meaning electromotive force. That got out of vogue because it's not really a force, okay, but it is. So it used to be P is equal to IE, and I can remember that because I love pi, okay, but never mind. But now it's P is equal to IV. So what would it be here? 0.5 amps times 120 volts, and that would be watts. Okay, good deal. Which is about like in standard incandescent light bulb, 60 watts. Fans they don't get very hot, not producing a lot of heat, so that's pretty small. Whereas, what was that, a hair dryer? Yeah, lots of heat. Look at the wattage. You'll watch that thing really turn, spin when you are using that. Okay. Table 6.2, though we've hit it all, but over different periods of time, I wish they had illustrated the table in the text. I think I'll go on and do it here. So I'll go and delete this. Can I delete these two examples? Okay. All right. Let me do this. Charge. What is the unit for charge? Or what is the parameter for charge? What symbol do we use for charge? Little q. Remember I said in the last chapter, chapter 4, Q was heat, but it's capital Q, little q is charge. And charge is equal to, that's a macroscopic concept, and it's N times E, where E is the electron charge. That's why I put a little minus on there, so you know you're talking about the electron charge, where N is the number of electrons. We did examples with that last time. Okay? Then we did what voltage was, and that's also potential difference. What symbol for that? V is equal to, and what is a volt? You've heard that before, haven't you? What is a volt? Okay, watt is, not watt, okay? It's work per unit charge, okay? Or I prefer E per unit charge, energy per unit charge. What unit for that? Oh, what's unit for charge? I didn't ask you that. The table doesn't give it, I'm giving it to you. Yeah, it does. That's the next thing. Charge is measured in what units? Y'all answered it earlier. Somebody did. Charge measured in what unit? French physicist Charles Coulomb. This is measured in coulombs. Energy per unit charge, that would be energy, joules per coulomb. And what's a joule per coulomb? It's a volt, okay? Sorry. Get back around where it started from. The next thing is that's electrical potential difference. Electrical potential difference. That's really the best word for, we say voltage all the time, but it's potential difference. Okay, current. What's the symbol for current? I. And what is that a measure of? How do we define current? It's, the unit is amp, but it's charge per unit time, which is coulombs per second, which is amps. Those are the units. Okay? Electrical resistance, and that's just ohms, which is a volt per amp. Let's write it down. Resistance is R, and that's equal volts per current, okay, which is volts per amp, which is ohm. That's the unit. Okay, and electrical power, okay, the unit for electrical power, watt. Okay, the formula for it is P is equal to IV, and that would be current, which is I is current, which is in amps, times volts, and the unit here would be what? Watt. Okay, very good. I wondered if anyone was here. Okay. Now, they have a little blurb, concepts applied, which really I found pretty interesting. And my wife wished I'd never read it. But it's on shocking costs, which they aren't really all that shocking. In fact, this really isn't appropriate. It's not what one I was thinking of. But it just looks at how much your monthly electric cost for watching television, cost of drying your hair with a blow dryer. Basically what they're getting at, anything that produces a lot of heat, there goes the cost upward. It's not the one I was looking for. I thought this was going to be talking about cost of AC versus DC. We produce alternating current much more cheaply than direct current. Batteries are actually fairly expensive. They may seem cheap, but for the amount of power you get out of them, not. And like I said, my wife would just as soon I hadn't read that, because anytime I can do something without using a remote, a battery, or something else, I do. And John's nuts. Okay. Never mind, that's beside the point. People behind the science, I've mentioned them a couple times recently. Good old Benjamin Franklin. You think of him as a statesman. He was the first postmaster general. He was a publisher. He was all sorts of different answers. He was one on the committee that wrote the Declaration of Independence. I think he was also on the committee that wrote the Constitution. He was just all over the place in everything political, but he was also a great scientist. Very seldom do you find that combination. They're talking about the science here. Okay? Not just electrical, he invented what they call the Franklin stove, which is still used today. Its common name is the potbelly stove. Much more efficient way of heating a room than a fireplace. He came up with that. The first person to come up with that concept. Everybody does it nowadays. So you've got incredible mind and guy here. Let's do example 6.7, and then we'll do 8. So I'm going to erase this. What is the cost? Now this is like that last thing we did, actually on this slide. What is the cost? So we're looking for cost That's not coulomb, that's cost, okay, of operating a 100-watt light bulb. What's that a measure of?
Power.
Power, because power is measured in watts. For 1 hour, what's that measured in? Okay, that's your time. Okay. If the utility rate is 10 cents per kilowatt hour, dream on. Okay, 0.10, 10 cents per kWh. Now they've almost given it a rate away now. That is what they're calling the rate. Okay, so you don't have to know that. So what's the cost? Now they gave you a really bizarre formula. Let's not do that. Let's just look at our problem here. Well, here you're given 100 watts as your power. Here you're asked to evaluate cost using kilowatts. So let's just go and get this watt into kilowatts. How do we do that? Second.
Multiply by 1,000.
Multiply this by 1,000.
Move the decimal.
Move the decimal how many places? No. 1,000. How many is there? 3. Which way do we move it? To the left. To the left. Okay, yeah. This isn't military. You move it to the left. And here's one way of remembering that. What you're doing is going from a small unit to a big unit. So therefore you go from big numbers to a small number. So if you're going to a bigger unit, you have to have a smaller number. So move it to the left. So that's 1/10 of a kilowatt. So this will be 0.1 kilowatt. Okay? And then from here on, it's pretty easy. What you have down here is a kilowatt hour. So to get a kilowatt hour, you multiply your power, kilowatts, times your time, which is in hours, 1.00 hours, and that gives you 0.1 kilowatt hour, right? Then multiply that by 10 cents. Oops, 0.10. This is dollars per kilowatt hour. And your kilowatt hours cancel out, and that gives you 0.01. 1 penny. 1 penny is what it takes to burn that 100-watt light bulb for 1 hour. Of course, if you do that each night, and you do it for a month, that's 30 cents. Still not a lot. But if you happen to burn it for 2 hours and a night for that, that would be 60 cents. So after a while, it does add up. And if you got more than 100-watt light bulbs on, that multiplies too. So it can add up. But nothing as much as the air conditioning, the oven, the hot water heater, anything that produces heat, go up a lot faster than that. Okay. That's why my younger brother who worked for the power company, he said, light bulbs, they don't cost anything. You can burn as many as you want. He had his house lit up all the time. I'm still cheap. I make Abraham squeal because I pinch him so much. Okay, let's do 6.8. Okay? So let's go down and erase this. 6.8. An electric fan draws 0.5 amps. What's that a measure of? That's your current, and we give it the symbol I. In a 120-volt circuit, what's that a measure of? Volts or potential difference, exactly. What is the cost of operating the fan if the rate is 10 cents per kilowatt hour? So again, we have the rate is 0.10, 10 cents per kilowatt hour. Okay? Now, they give you current and voltage, but we don't have kilowatt. And let's see, they're asking for what is the cost of operating the fan, and this will give you so much per hour, because you'll see that comes up. They give you current and voltage. What can you get out of that? Power. Okay. How do we get that? P is equal to IV. Okay, and that would be 0.5 amps times 120 volts, which would give you 60 what? What? Okay, very good. Okay. Now, to get that to kilowatts, because that's what you got down here, what do? How many places? Which way? To the left. Very good. So you multiply, 0.060 kilowatts, you just changed it to kilowatts, times 0.10 dollars per kilowatt hour. I can't write, goodness gracious. Okay, because this is in kilowatt and that's kilowatt hours, so the kilowatts go out, and this gives you 0.006 or 0.6 of a penny per hour. Okay, so if the fan only drew half an amp on a 120 volt circuit, you could run it for 2 hours and still cost less than 2 cents. Okay? So yeah, not a lot. As far as ceiling fans, if you got a switch on that, if that can keep you cooler feeling than running the air conditioner down another degree or two, much, much cheaper. As Daddy used to say, right? All right, so 0.6 of a cent per hour. Okay, we've already done that. All right, where are we time-wise? Did you let me go past 3:15? You did, didn't you? Shame on you. We need to pause here. What three main components do we need in a circuit?
A voltage source.
What?
Voltage source.
A voltage source. In this case, it's a power supply, we call it. Acts like a battery. And what else?
Negative and positive.
Okay, well, that has a negative and positive on it. Okay? That's one thing. Voltage source.
Load.
A load. Okay, we're going to have light bulbs for that. And what else? That's part, maybe, but what's all in your hand? A wire. We have to have the pathway, right? So those are the main three parts. Now here they give some of the symbology. Okay, that's what a circuit is. It carries, the pathways carry the electric current, which is charge per unit time. That's what current is, charge per time. Okay? They give some of the common circuit elements here. Your battery is usually a series of long line, short line, long line, short line, long line, short line. That indicates a battery. Supposedly each pair is a cell in the battery. Doesn't have to be, but quite often it is. Notice the convention here. Is everybody listening? The convention here is that the positive is on the first long side and the negative is on the outermost short side. Okay, that's the convention. Now, if you're talking about a ground, which I've heard several times, your ground symbol is this. We're not going to necessarily be using the ground, but I know a lot of you do. A resistance in general is going to be a jagged peak, a series of peaks. When they put a circle around it, that usually means it's a light bulb. But that is a resistor. That's your load. Okay? Now, if you had a variable resistor, they put a line through it, meaning you can vary it. We're not going to do that. Now, they have switches here. We have some switches, but I chose not to use them. But you'll see them on the diagram as switches. We'll just assume they're always closed. Okay? Now, and we don't have this on our diagrams either, but if you ever see two wires crossing with a little hump on it, that means they cross without being connected. But if they cross being connected, then there's a little dot meaning they are connected. We're not going to mess with that either. Okay? Now, it says with one flashlight bulb, one flashlight battery, one flashlight bulb, and one piece of hookup wire. We're not going to do that, okay? Don't worry about that. But what I want you to do instead of that is turn to the page 180, that's the back side of the first page. And what I want you to do, now everybody listen to this. Because people get this confused, and it's really, really simple. What I want you to do is draw your circuit number 1, just like you see it down here. Draw it in this box right here. Draw circuit number 1 in the box. You can even leave the switch out of it if you want to. You don't have to put the switch in it. But basically, just draw that diagram. Number 1, draw it inside the dotted lines here. Okay? Does everybody hear that?
Yes.
Are you drawing it?
Yes, sir.
Okay? It doesn't appear to be. Okay.
Number 1.
Okay. What do you notice about the battery? 1 short line, 1 long line. You know what that means?
1 cell.
Second?
1 cell.
Okay, yeah, 1 cell. But what does the short line represent? The negative side, the long line, the positive side. Okay? You don't even need the switch in there. If you want to draw it, it's fine. It doesn't hurt anything. But it's just a real simple thing to draw. Okay? Now, if you drew the switch, imagine the switch is closed. That's why I said you don't need to draw it. Okay? Now, what I want you to do then, and this is the second part of number 1, draw an arrow to show the flow of the conventional current and a second arrow to show the flow of the electron current, and identify which is which. One arrow will be which direction the conventional current is going. The second one will be the direction the electron current is going. We saw one like it in the text. I harped on it several times. Hopefully you were paying attention and you can draw the arrows correctly. Any questions? You want me to look at them just to make sure you got them right? Very good. Got it? Got the arrows yet? Conventional and electron. Excellent. I think so. Your battery almost looks like a ground there, but just one long line, one short line. Always the same. All right. The question is, how do you draw an arrow? Okay. Something like this. Okay. Second, one arrow needs to be the conventional current and one the electron current. Anyone want me to look at theirs? Okay, I see 2 arrows, but I don't see them labeled. Which is good. I'll write it down. And the other is electron. My question is, what's the difference? One of the you got to take that Okay, well, more recently we did it in the book, and they had the thing. You remember what is the electron current? Or is it what it's trying to do? What's the charge on electron? Charge on electron. Negative. So that, that would have to be the other way. Everybody got it? Anyone still want to look? Okay? Anyone else want to look? Everybody got it? You got your book from here? conventional current is going from what to what? What makes it conventional?
Negative positive.
Conventional is positive to negative.
Negative, my bad.
And electron is negative to positive. And if you have your lines right for your batteries, with the long line being the positive, the short line being the negative, and some of your lines look very similar in length, but I can see a little bit, then the conventional is going from high potential to low potential, from plus to minus, whereas the electron's going minus to plus, the opposite direction. Okay, everybody got that? All right. Now the next thing I want you to look at, and every team has one of these. Theirs has wires on it, yours do not. But you'll see a light bulb, okay? By itself, not on the little square, but by itself. This one has wires, the others do not. They're near your apparatus there. And you'll notice that the light bulb, if you look at it closely, sometimes it's hard to see through the glass, you'll see there's a filament that connects two prongs. Everybody see that? Now, this one happens to have wires connected, has one wire connected to the tip at the end. Does everybody see the tip at the end of the light bulb? The base end. And the other wire is connected to the metal that's around the bulb. But notice what's in between. Black plastic. What is that? An insulator. It doesn't allow current to flow. So, what you have here in your picture, next to the block that you just filled out, you have a bulb that looks somewhat like the bulb that you have there. Here's the two prongs. There's a filament in between, but that bulb will not light. Why? Yeah, you don't have a complete circuit. It's not hooked up, okay? Now, these two prongs, one needs to go to one place and one needs to go to another place. Any ideas where they may need to go?
Side goes negative, bottom
Okay.
goes positive.
Okay, well, you can't tell a positive and negative here. It really doesn't matter. This is probably going to be, it could be DC. But see, one is going to that tip and the other to the edge. Now you can have a complete circuit. Once you put a voltage supply, a power source, whatever you want to call it, across there, then the bulb will light. But one of these prongs goes to the tip and one goes to the edge. You know what I'm talking about? You just need to draw two lines, one from one and one from the other, and let me see what you got. Perfect. You understand what I'm asking?
Golly.
Okay.
We still on break.
Okay, now you have them connected. One is the way to there, and one is to the tip.
Yeah, it kind of hurt.
You overthink it, you're like,
Where's the guy who's at?
we're on the break.
One goes to the edge, and one goes to the tip. And everything they touch across. Okay, we're still there. Let's to the edge.
Oh, you come from bottom side. I don't even know we spilled them, so. Like a stack of styrofoam. Like a McDonald's. That's so bad. It's still have a small drip.
You can't see where it is. One of them goes to this part,
And there are the ends covered in it.
now one touches each other. Otherwise, you don't. All right. Anyone else need me to see yours, or are you confident with what you got? Okay, good deal. Okay. We're back to page 179. You've done one, you've done two. Okay. Number 3, I'm going to set up for you the first time. It says, why are the circuits shown? Okay? So, what I want you to do, hand me the thing you were playing with. Good. That's right. Alright. Oh, yes, I see. I call it a mess, not a circle. Okay? Okay. Now, if you want to look at what I'm doing, I'm putting the red in the red. And then the black and the black. And that here. Now, what you have to watch for, you see, this shows the circuitry. So you can actually see the soldering going there. So it's going from this to the rest of it. That's why you don't go here or somewhere else. You have to do that. Okay.
It was already.
Here's the gap here. You see the soldering under there? Here. Sorry, I didn't have yesterday all right, we're back here. What this out to? Okay, here's the power screw coming off. I don't want to burn out the bulb. Okay? If y'all haven't already noticed this, here's the on-off switch. Comes up the voltage. And turn it on. Get that. Okay. Now. Okay, don't run it very high. Turn it down. Turn it down. Okay, turn it off. Okay. Now. Okay. Every team saw how I operated what I set up is your circuit number 1. Okay? Now. Okay. Listen up now. When you turn on the switch, okay? Listening? When you turn on the switch and turn up the knob until you get the bulb not real dim, but not real bright. Just sort of a standard brightness. I want you to look at that and understand that's the standard brightness. Let me look at it before you decide. And when you get the standard brightness, then read the voltage off the screen down here. Okay? So that's what you're going to do. So turn on the switch, turn on the rheostat, turn it up until you get just a little bit. Not super dim, Turn it up a little more. Okay. Something sort of standard. Maybe just that looks pretty good. What you got? Okay, that seems reasonable. Whoa, that's pretty bright. Turn it down.
Really?
Turn it down. Turn it down.
Wow.
Okay. A little more. Down.
I'm going down.
Okay. Some of these are really.
Look at that logo. 20 volts.
Turn it down. Turn it down. Okay, wait. This one's sort of unstable. Okay, turn it up.
Trying to turn it up.
Turn it up. Turn it up. Turn it up. Okay.
Oh, he did. So
That's going to be your standard brightness. What y'all got?
You reckon there's no resistance? Yeah, for a light bulb.
That's 4 volts. Take a look at your bulb and know that's your standard brightness. Okay, you turn yours off.
That was the max you had to. It went up to 13, but it's still in the right place. I just wonder, there's people across the room.
Okay, that's your standard voltage. Standard brightness. Okay, now over on page 183, under circuit 1, it's asking for observations. Well, 2 observations you put here: standard brightness, and you put down your voltage. Okay? Now, what's that going to represent for you? Turn back to page 180, and you notice that's a single cell battery. So we're going to say your voltage is what 1 cell battery is. Okay, that voltage is going to represent a single cell. Okay? Now, once you've recorded that and observed it, turn it off to save your bulbs. I don't have but a limited number of bulbs, so save your bulbs once you've seen the standard brightness. Okay. Everybody got that recorded? Standard brightness, and you saw what that was, get it in your mind, and then what the voltage was. Okay, you describe to me what number 2 is.
Open circuit, got a dead cell in the battery.
Say again?
Dead cell in the battery.
No. It's just a single cell in the battery. They just threw it further apart. Single cell in the battery. So therefore, your voltage is going to be the same that you just had, whatever your standard was. So you're not going to change your voltage. But what do you change in this circuit?
Load.
Add a bulb. Okay? So pull out your black. And where will you put the bulb? You don't need that. No, not that bulb. This one. Okay? If you do, you're going to have to add some wires. Actually, you could be really cheap about it and put it right there. And therefore, it's connected to the same bar as this one. And then you take this and plug it. You plug it wherever you think it will be. Okay? Let me see how you set up. Excellent. Let me see how you set up.
Yeah.
Yeah.
I don't bother having them.
What you can do is all right. Okay. Now I hope you didn't change your voltage setting. So turn on the power, and what you're to observe are 2 things under your observations. Okay? Turn it on, leave it on. Okay? For a moment. Make sure you're at the same voltage, your standard voltage. Everybody at the standard voltage?
Yes.
Okay? Here's the 2 things you observe. Number 1, are your bulbs, and here's the 3 choices: brighter, dimmer, or standard?
Dimmer.
Everybody see that?
Yes, sir.
Okay, so that's one thing. Here's the second thing you observe. Remove one bulb without changing anything else in the circuit and see what happens to the other bulb. So just pull one bulb out. No, leave it on. Pull one bulb out and leave it on. Yeah. Okay, pull one bulb out, and what happens to the other bulb? What's that? It doesn't come off. It goes off too. Hey, you weren't supposed to pull that out.
Oh, I didn't got them.
Okay. Okay. What happens when you pull the bulb out? Not this. Pull the bulb out. No, that's the whole square. What happens to the other bulb? It went out. Okay, good deal. All right. Now. Okay. Everybody listening? Oh, what did you write on the table? You write two things down.
Dimmer bulbs.
Dimmer bulb and
Both went out.
both went out. Very good. All right. Set up number 3. But don't change your voltage yet. Set up number 3. How does number 3 look? Okay, you don't need that for number 3. Look at number 3. What do you notice here? Okay, yeah, now don't double your voltage. That's not what I don't want you to do. But you go back to a single bulb and wire it the same way you had number 1. And then what I want you to do is increase the voltage just a little bit past what you had number 1. Don't double it, just increase it past it. So what do you notice about the bulb? Brighter? Okay. So for number 3, only one observation. The bulb got brighter. Okay, now that's called 2 batteries in series. We haven't talked about series yet, but we will later. Once you see that, you can turn it off. I don't want you burning out the bulb. So everybody saw that? And the only observation, because you only had one bulb, was the bulb get brighter, dimmer, or stayed at standard. Okay? Yes. Then set up number 4. And what do you notice about number 4? Okay, you're doubling the voltage and doubling the load. Okay, so go back to the same as number 2, but this time you do double the original voltage. You don't have to worry about this. Double the original, not what you had. What was your original voltage? 7. Okay. What do you notice about the brightness of the bulb? Then what? Okay, we're not comparing the 2. We're looking at the standard. How do they compare to standard? They are brighter than standard? It looks like standard to me too. So that's what you write. Standard brightness. And what happens when you remove a bulb? Well, tell me. Show me. The other one goes out. Okay? You can leave that out if you want to, or turn it off once. Don't just leave it running. Okay. Everybody get that? Number 4? Huh? Okay. What did you find about the brightness? Did y'all get them? Okay, well, approximately what's your brightness? Okay, but you're at more than double voltage.
We're trying to get the values.
Okay, somewhere there. Okay, let me try. That's close. What do you know about the brightness? Standard brightness. What happens if you remove the bulb? Yep, the other one goes up. Excellent. Okay? That was number 4. Now, what do you notice about number 5?
Parallel.
Okay. For those who know electricity, that's called the parallel circuit. How do you reckon you're going to wire that one? Okay, yeah, you're going to need some wires on this one. Okay? So you try to set it up to wire the parallel circuit. Let me look at it before you do anything else, and then I'll let you hook it up. Okay, you use these wires. Okay. You can't leave them like that. I'll guarantee you that. Okay?
Where did that come from? Speak for yourself over there.
Hey, if you think you got it set up, let me see. Okay, let's see. Coming in, your high side here, high side there, low side here, low side there. Low side there.
You don't understand. He don't even know what he's saying. Hey.
Okay, what you notice you got, everybody got your wiring done? Let me see, I haven't seen yours yet. Yeah, you need to have the low side connected.
Hang on, we still on. I'm sorry, man. We're talking about it.
I'm just curious.
Okay, let me see. High side is connected. And the low side is connected.
I'm looking at that four-wheeler in the back.
Okay, now what's the battery on this one? What's that?
I don't think it is.
24. Wait, what is your battery? 3.5. Yes, your original, your standard. Okay? Everybody understood? Okay? Now, what can you tell me? First about the brightness. Standard brightness sounds good. What's the other thing you observe?
One light goes out, one stays good.
Good, show me. Very good. All right. What do you notice about the brightness? Standard. What happens if you remove one?
The other one stays with
Show me. Let me know you did it. Yeah, look at that. You did it. Okay. Okay. What happens if you remove one? So as you finish, turn it off. Well, don't take it down though, because look at number 6. Oh yeah. Are you putting all this information in the table?
Yes.
Okay, be sure you get your observations there. Okay? Now, number 6. How does that differ from 5?
Battery cell.
Okay.
Double.
Now this time, don't double the battery. Just increase the battery. Getting ahead.
Whoa, Joseph, way too bright still.
Okay. Just increase the battery and what you know. Just increase the brightness of the battery and what you know. Don't need to double it. What happens? Get brighter. Okay? And remove a bulb. One stays on. Okay? Turn it off as soon as you're through. Okay. Now, we are not going to do number 7 physically. No, we start with 7. We're not going to do 7 physically. What would you do if you were going to do it physically?
You would wire it up, short it to ground, and it would just not.
Okay, yeah. You would take out one bulb and just connect a wire from high side to high side. What do you think is going to happen? I heard you say something.
Nothing.
Okay?
I think the path of least resistance, you don't see no light like that.
Okay, but you said it was something.
Short drill.
Okay, not quite.
Short drill.
Okay. Goodness, I'm losing my term here. No, you're right. You're right. It's a short circuit. Okay? and JJ gave exactly the right explanation. The bulb doesn't come on because, think of this, folks. Think of charge as being like students. They always take the path of least resistance.
Amen.
Don't they? Okay. So, the charge, rather than going through the battery, through the light bulb, which has a high resistance, it goes through the wire, which has low resistance. So, no current goes through the light. It all goes through the wire. If you did turn it on, the wire would start getting very hot. You didn't do it. Okay, good. Would get very hot because you have what they call a short circuit. Now, how would that differ from having the wire disconnected?
Because you got voltage.
That's called an open circuit. Your bulb doesn't come on, but it's for completely different reasons. An open circuit will never cause you to have a fire, I don't think. A short circuit will. Because now you have a wire or something heating up like crazy because there's very little resistance, lots of current, lots of heat. You can start a fire. And open circuit is one that no current flowing at all. Nothing will work, but nothing works as well. So, what it asks you to do here on number 7 is on page 183, it says, one bulb in parallel with the wire, show with arrows how the current takes the path of least resistance. So you show with the arrow. You can either use the figure on page 180 or draw it in the block on page 183. I don't care what you do. And show with an arrow which way the current flows. Does it go through the wire or through the bulb? Show where the current goes. Does everybody understand 7?
Yes.
Okay. Any question on 7? Okay. Now, if everybody's finished with 7, when you are, look up at me to let me know you're through. Okay. Now, number 8 basically is just like number 6. Double the voltage. It just shows a different connection there. It just shows 2 switches rather than 1. We're not using any switches, so basically number 8 is the same as 6. So answer the questions the same as you did for 6. Okay? Make sense? Oh, the same voltage, same setup, just they use 2 switches, we're not using any switches. Okay. Now, my question to you now is, the rest of this lab is spent answering the questions on page 181 and 182. There's 7 questions there. Okay? Do you want to do it in here in your group, or would you rather go to the classroom and do it there? I don't care. You want to do it here in the group. That's fine with me. Just look uncomfortable. Now, let me point this out to you. Listen up, people. This can lose you points. Okay? Number 1, all it says is using the brightness of the bulb in the simple circuit, circuit number 1, as the standard for normal, describe which circuits had bulbs of normal brightness. Okay? Okay? So that's the answer to number 1. You look at your table on page 183 and see which ones had standard brightness and put down those circuits there. Right? That's all your answer to number 1. Put down the circuit numbers that had standard brightness. Okay? You don't have to do it now. I'm just asking you to understand. Okay. Question number 2. Notice there's 2 parts to question number 2. There's just one part to question number 1. Number the circuits that had standard brightness. Number 2, which circuits had bulbs that were dimmer than normal? That's the first part. The second part says explain. You've got to do list of circuits that had dimmer than normal, but then you also have to tell me why. Yes?
If the bulb is off, is that included?
Yes, you can put that one in there. Okay? You don't have to, but I think it's a good idea. Anyone have any problem with the explanation? Got it? Okay. You don't have to have all the answers now. I just want you to understand it. Number 3, which circuits had bulbs that were brighter than normal? Okay, look at your table, see which ones are brighter than normal, and write those down. Okay? The number of the circuits. But on that one, you also have an explain. If you don't explain, you lose points. Do you know how to explain that?
Yes.
Number 2 and 3 have an explain on it. You have to tell why on number 2 you had circuits that were dimmer than normal, and number 3 why you had some circuits that were brighter than normal. Okay? Notice number 4. In which circuits did removing one bulb cause the other to go out, but you also have to explain. So list the number of circuits that the second bulb went out, but also explain why. Number 5, same deal. In which circuit did removing one bulb not affect the other? And then you explain why. So if you don't do the explain, you're going to lose points. Okay? And then number 6 is a question I think we've answered like 2 or 3 times today already. Describe the general requirements for any circuit to function. And then number 7, you just have to answer any way you want to. You just have to have an answer. If there's no answer, you lose points. If there is an answer, you get credit. Number 7. That says, what is the purpose of lab accomplished? You answer that honestly. Okay? Does anyone need your setup any longer? Okay? If you have any questions, please ask me. I'll be glad to answer. Yeah. Okay? And I think Courtney was looking for a while. Huh? You did? Huh?
What number?
4? Did you get the actual
Just any of the ones that whenever you pull the one bulb out, some went off.
No, she's supposed to take No.
What I did.
Jerry always talk about that. When you pull it out to
Again, if you have any questions, ask. Don't be guessing. Ask. Now, let me look. Lab 1, I think I've returned to almost everybody. Can I go on it? Was there a question? I'm going to go on and pause the recording if it's okay with y'all.